Hello everybody. In this video we are going to learn integrals that requires partial fraction decomposition. We're going to go through decomposition of n of x over d of x, distinct linear factors, repeated linear factors, mixed linear and quadratic factors, and repeated quadratic factors. Let's start with decomposition techniques. Our first rule is always to divide if the fraction is improper. What do we mean by improper fraction? If the numerator is greater than the denominator, let's say 5 over 3, then we have to divide this fraction, and 5 divided by 3, 1 times 3, and 2 is the remainder, and denominator does not change, so 5 over 3 is equal to 1 and 2/3. So we converted improper fraction into mixed numbers. So we're going to use this knowledge, and let's say we have x to the third plus 2x plus 5 over x plus 1. Here our numerator is greater than the denominator because the degree of x to the third, is higher than degree of x here. So for this we had to use either long division method or synthetic division. Either works. Synthetic division. So the focus of this video is partial fraction decomposition, so I'm not going to go through long division and synthetic division in detail, but if you guys demand, I can do separate video on long division and synthetic division. But if the fraction you are decomposing is improper, you definitely have to divide numerator by the denominator until it is not divisible anymore. Now let's see the different type of factors in the denominator and how we convert it, like 5 over 3 is equal to 1 and 2/3. So let's say we have some numerator over some factor x plus 1. So if we have linear factor, which is x plus 1, then our numerator will be some constant a. And we know that this fraction is equal to this fraction, then we're going to solve for a using some techniques we will see soon. If we have an x, some numerator over x plus 1 to the second power, this is still linear factor because x plus 1, x to the first is the linear, but it is repeating x plus 1 squared, which is x plus 1 times x plus 1, which is repeating linear factors. In this case, we had to write x plus 1 for the first factor. We have two factors here, and some constant a on the numerator. Because this is linear, our numerator will be 1 less degree than this, which is constant, plus for the second factor we had to use x plus 1 to the second and another constant b. If we had n of x and x over x plus 1 to the third, which is linear factor repeating 3 times, then it would be some constant over x plus 1, some constant over x plus 1 to the second power, and some constant over x plus 1 to the third power. So this is still linear denominator or linear factors. If we have, let's say x plus 1, x plus 5 to the second, and let's say x squared plus 5. Here we have 1, 2, 3, and we have here 4 factors. One factor is x plus 1, which is linear factor, so we have to use some constant a for the numerator. We have x plus 5 repeating, so for the first factor we have to use some constant b. For the second factor, x plus 5, we have to square it, some constant c. This is quadratic factor, so we have to use some linear numerator, and linear is some ax plus b, or here we used a, so we have to use the x plus e. If we have like x to the second minus 3, this is a quadratic denominator, so we have to use linear numerator. We keep the denominator as it is, or the factor as it is, and for the numerator we have to use some ax plus b. Because this is quadratic, numerator has to be 1 less than that, which is linear. Now let's see on the applications. Okay, let's say we have to take the integral of 1 over x squared minus 5x plus 6 dx. So we see that this is not improper fraction. Numerator is less than denominator. So we go ahead and decompose the denominator and split it into the factors. So x squared minus 5x plus 6 is equal to, we need two numbers that multiplies c term, which is 1 times 6 or 2 times 3, and two numbers that adds up to b term or middle term, which is negative 2 and negative 3. So x minus 2 times x minus 3 is equal to x squared minus 5x plus 6. So I can replace the denominator with these factors. So 1 over x minus 2 times x minus 3 dx is our new integral. Now, using the partial fraction decomposition method, 1 over x minus 2 times x minus 3, we are going to equate this two different fractions because we have two factors here. So this is like n of x over d of x is equal to, our first factor is x minus 2, our second factor is x minus 3. For the first factor, we are going to use some constant a, because this is linear, we use constant. For the second factor, x minus 3, we're going to use some constant b, because this is linear factor again. Now we know that this fraction is equal to this fraction, like our 5 over 3 is equal to 1 and 2/3. So now we're going to solve for a and b. Our first step is to multiply whole equation by the LCD, which is x minus 2 times x minus 3. If we multiply x minus 2 and x minus 3 at the same time with the first fraction, we obtain only 1. Because x minus 2 cancels out, x minus 3 cancels out, 1 is left. If we multiply LCD, least common denominator, with this fraction, we obtain a times x minus 3, because x minus 2 cancels x minus 2. Plus, if we multiply LCD with b over x minus 3, we obtain b times x minus 2, because x minus 3 is cancelled out. Now we have 1 is equal to a times x minus 3 plus b times x minus 2. Here we're going to use 101 rule, giving some value for x. So giving value is one of the first techniques that you can apply. So let x be equal to, so you're gonna pick up some number that will totally cancel out one of the terms. Let's say x is 3. If x is 3, then it will be 1 is equal to a times 3 minus 3 plus b times 3 minus 2. And if we simplify this, 1 is equal to 0, because a times 0 is 0, plus b. So here in this equation we find that b is equal to 1. And let x be equal to 2 this time. And if x is 2, then 1 is equal to a times 2 minus 3 plus b times 2 minus 2. Here this term is gone because 2 minus 2 is 0 times b is 0, and 1 is equal to negative 1a, so 1 is equal to negative a, so here a is equal to negative 1. So now we know that a is negative 1 and b is 1. So let's replace a as negative 1 and b as 1. So our new integral will be negative 1 over x minus 2 plus 1 over x minus 3 dx. Now we know how to integrate this and that separately. First we can separate the integrals. Negative integral 1 over x minus 2 plus integral 1 over x minus 3 dx. Here you can either use u substitution, which is let u become x minus 2 and let u become x minus 3. Then du will be dx, the derivative of x minus 2 with respect to x, and derivative of x minus 3 with respect to x. You can go either u substitution, or you can practically think that 1 over x is the ln, antiderivative of 1 over x is ln. So this is like ln of u times derivative of u. So which is like ln of x minus 2 times 1, because derivative of x is 1 plus c. So practically we can take the antiderivative of this as negative ln of, because we have negative sign here, x minus 2 plus ln of x minus 3 and plus big C for all of them. So that is the solution for this integral. So here we use the partial fraction decomposition method, and we equated 1 over x squared minus 5x plus 6 into these two factors, and then we solved for a and b, giving some value for x, and then we obtained that 1 over x minus 2 and 1 over x minus 3 as the equivalent integrals, and then we solved for these integrals. And here you can use small u substitutions, or you can practically think that 1 over x is the ln times derivative, this is the chain rule, ln of u times derivative of u. This time let's see repeated linear factors example. Okay, let's try to evaluate 5x squared plus 20x plus 6 over x to the third plus 2x squared plus x dx. Our first rule is always to check if the numerator is greater than the denominator. Here it is not, because x squared is less than x to the third. So our aim is to decompose, make the denominator into factors. Okay, so we have x to the third plus 2x squared plus x. So we can factor this out as we can factor out x because we have x common in all of them, to the x squared plus 2x plus 1. Let's keep it as numerator for now. Okay, let's see if we can further factor this out. We know that x squared plus 2x plus 1 is x plus 1 to the second, because this is perfect square trinomial. Or you can think that two numbers that multiplies c term, which is 1 times 1, and adds up to middle term, which is 1 plus 1. So in either case, it's going to be x plus 1 times x plus 1. So you can rewrite it as x plus 1 to the second power. So it's going to be 5x squared plus 20x plus 6 over x times x plus 1 to the second power is equal to. Now for the first factor x, we're going to use some constant a, because this is linear x to the first. So we need a constant on the numerator, plus this is repeated linear factors. So for the first repeated linear factor, we're going to use some constant b, and for the second linear x plus 1 to the second, we need to use some constant c. Now we're going to solve for a, b, and c, and then substitute this fraction with the right hand side. So for this, we're going to multiply whole equation with the LCD. This is our LCD, least common denominator, x times x plus 1 to the second. If I multiply LCD with the first fraction, I obtain only the numerator, because this cancels that. So 5x squared plus 20x plus 6 is equal to, and if I multiply this with this fraction, a over x cancels x, then I'll have a times x plus 1 to the second power. If I multiply b over x plus 1 with the LCD, the first factor cancels, then I'll have b times x plus 1. And if I multiply this with the LCD, that cancels, so cx. Now I have this equation. Here you can either give some value, arbitrary values for x, or you can equate terms. Here, now we can give some values for x arbitrarily. So here, let's pick x as 0. If x is 0, then left hand side we're gonna be left with 6, because 5 times 0 squared plus 20 times 0 plus 6. And here 0 plus 1 is 1, 1 squared is 1, 1 times a is a, plus this is going to be 0, and that is going to be 0. So here a is equal to 6. We solved for a. This time let's pick x as -1. If x is -1, then this is going to be 5 minus 20 plus 6 is equal to -1 plus 1 is 0, this is gone. -1 plus 1 is 0, this is gone, and this is going to be -c. So it's going to be -15, -9, c is -9, so c is +9. We solved for c as well. This time we know a and c, so we can give x any value and then place a and c. So let x be 1. So 5 times 1 squared is 5. 20 times 1 is 20. Plus 6 is equal to, we said x is 1. 1 plus 1 is 2. 2 squared is 4. 4a. And we know that a is 6. Plus x is 1. b times 1 is b. And this is going to be 2. It's going to be 2b. plus c times 1. We know that c is 9. 9 times 1 is 9. So this is going to be 24, and 25, 31, 24, 33. Subtract 33 on both sides, so it's going to be negative 2 is equal to b, then b will be equal to negative 1. Now we know a, b, and c. We can substitute a over x will be 6 over x. So our new integral will be, instead of a over x, we have 6 over x. B is negative 1, so let's use directly negative. Negative 1 over the second factor is x plus 1. And the c term is 9. 9 over x plus 1 to the second power dx. So now we know that this original fraction, the question, is equal to this 3 different fractions using the partial fraction decomposition method. Now we know how to integrate these each fractions. So I leave the small integrations to you. 6 over x is the ln, 1 over x plus 1 is the ln, and here you're gonna use the u substitution. Let u be x plus 1, so you can also integrate this. So I'm going to separate it into 3 separate integrals. 6 times 1 over x minus integral 1 over x plus 1 plus 9 times 1 over x plus 1 to the second power dx. Alright, so our aim was to do it in partial fraction decomposition, and after this point we know how to integrate this. This is going to be 6 ln of x minus ln of x plus 1, and this will be negative 9 over x plus 1 plus c. So I can directly write it actually. Ln of, this is going to be 6 ln of x, and this is going to be ln of x plus 1, and this is going to be negative 9 over x plus 1 plus c. Let's finish this video here, and in part 2 of partial fraction decomposition series we can continue with distinct linear and quadratic factors mixed and repeated quadratic factors. So see you at part 2.